Lovely. So we move to the next session, and the chairman is Max.
Max. Okay. Thank you. Thank you, Vice. This is Max Baliani speaking. I chair this session. We have three talks. We have the first speaker is a colleague of mine, Fabio Barufaldi. The title of this presentation is Medical Imaging Research at LTM. Fabio, are you there?
Okay. Can you see my slide?
Yes.
Okay.
Yes, the floor is yours.
Okay, we can move on. Again, good morning, everybody. I'm Fabio Barufaldi, one of the senior researchers at the Medical Technology Lab. As I told you before, during the welcome session, I've been working at the lab since 1991. And it is now my pleasure to give you a quick overview of the imaging research that we have done in the lab in the last 30 years. You know that imaging is an essential tool for orthopedics since the very beginnings of this medical specialty. Here you can see the very first X-ray picture taken at the Ritual Institute in 1899, at the just a few years after the discovery of the X-ray made by Professor Röntgen. In the meantime, tomographic methods such as computed tomography, magnetic resonance have changed dramatically the way we can see inside the body, and of course also the way we make research. Well, I'm going to summarize something like 30 years of medical imaging research at the lab, starting from the 90s and trying to give you an idea of what is going on right now. In a first schematic representation, I would say that my imaging research are mostly focused on two lines. The first one dedicated to the so-called health technology assessment for the introduction of new technology, and the second to support the multi-scale musculoskeletal modeling based on tomographic methods such as the classical methods, clinical CT and MRI, but also based on some laboratoristic methods such as micro-CT and synchrotron light. Okay, here we are with the first example of health technology assessment research that we started in 1996. That was the PSNet project. It was dedicated to telemedicine application orthopedics. I have to confess that I was very excited, but also pretty scared to be involved in my first European project. But at the end, it was a very excellent training for the international project that we had in the following years. At that time, the idea was to show that ISDN video conferencing system were suitable for telemedicine orthopedics. I know, of course, that for the current standard, a bandwidth of 128 or at the best 384 kilobit per second seems, is ridiculous, a ridiculous bandwidth. But we were able to demonstrate that under controlled protocols, the technical quality of the European ISDN network was sufficient to provide a first level of real-time telemedicine services in orthopedics. Well, we demonstrate in the first European project the technical feasibility of telemedicine in orthopedics. So what? You probably know that the Ritual Institute is a center of excellence for orthopedics in our country, which means that something like half of our patients are from outside of our regions, Emilia-Romagna. So they have to move by car, by train, by boat from Sicily, Sardinia, Campania, and spending time and money and to arrive in Bologna. So the general director of the Ritual Institute of that time was categorical. You showed us that the technology is fine. Now we have to start to activate a real services. And that was the aim of the second project, the teleconsulting project sponsored by the Health Ministry, where we had to face with completely different problems like the definition of a national network of points for delivering the services, or the professional engagement of orthopedic surgeons, or how to measure the satisfaction of the patient, or problems like the definition of organizational guidelines and very important tariffs for the services. And during the project, we were able to provide real-time teleconsulting to more than 3,000 patients living in the southern regions of the country. One more project related to health technology assessment is from the significant change that we had to face about 15, 20 years ago, when we had to move with the transition to digital radiology and PAC system for the entire Rizzoli Hospital. Well, you know that orthopedic surgeons were confident at that time in conventional radiology on film. That was the way for more than 1 century. And therefore, we had to guarantee to the surgeon that the diagnostic accuracy of the new digital methods were equivalent, at least, to conventional methods based on film. As, for example, in the very important preoperative planning of joint arthroplasty. And that was the aim of this project. Okay, now we can move talking about musculoskeletal modeling from, in this case, CT scan, where you have to provide bone density and bone morphometric information to support clinical activities such as preoperative planning for arthroplasty, or complex bone tumors preoperative planning, and long-term bone tumors evaluation and evolution. Another example of this clinical application is personalized bone fracture risk analysis, and a very good example of this application was implemented within the European VPH-OP project, a very important project, where the musculoskeletal modeling was aimed to predict the bone fracture risk for osteoporotic patients. Well, the generation of musculoskeletal model is a complex chain of very many different competences, and the way my group was supporting that generation was mostly in controlling the quality of CT information and for the evaluation of the safety of the patient. And quality means, for example, the definition of a specific protocol for bone mineral density calibration. And on the other hand, the safety means, safety for the patient means a proper evaluation of the X-ray dose that we give to the patient during CT scan. But patient means also, for example, how to control metal artifacts due to the presence of metallic implants. And in this case, new methods such as dual energy CT are very effective way to reduce these artifacts. If we control the quality of CT information, well, we are just at the first step for the generation of accurate numerical model for the prediction of mechanical properties of bone. Here you can see a reference for BoneMat, a quite popular software created within the lab and now maintained by our colleagues at the Bioengineering and Computing Laboratory, led by Fulvio Taddei. And the software is available for the scientific community. And BoneMat permits to transform the map of the voxel generated by the CT scan into a map of Young's moduli with the appropriate mesh required for finite element analysis. Next, okay. When we say multi-scale modeling of bone, it means that we have to investigate also the micro and the nanoscale to fully understand the biomechanical properties and phenomena like bone remodeling. Of course, in clinical CT, it is not possible to exceed the millimetric resolution on living patient due to dosimetric consideration, but micro CT can give us structural information on small samples with the resolution in the order of microns. You can see a very nice research line dedicated to the relationship between the microstructural parameters and the mechanical strength of trabecular bone. The question was why and where a bone fracture starts and proceeds during a compressive destructive testing. In addition, a very important facility for the biomedical research is the synchrotron light, providing us a very intense, high quality X-ray beams. In this case, we were among the very first to make a micro-CT investigation based on synchrotron light in 2006 on a femur with a very large field of view of 130 millimeters. Well, synchrotron light means also many other different techniques. Bone, we know that bone is a very interesting composite material with a hierarchical structure packing together collagen and mineral phase. And small angle and wide angle X-ray scattering can investigate the packing of the collagen and mineral phase, giving us the information of the mineral orientation at micro and nanoscale that work that we did in 2012. The last few slides about what's going on for medical imaging research in the lab right now. This is the European project MIMAS currently running that is dedicated to thermal effects of MRI on metallic prosthetic device. Well, in this case, we have a huge number of active variables on the thermal effects, depending, for example, on the MRI field, depending on the specific MRI sequence that we are going to apply, depending on the type of metallic device where the device has been implanted, and of course also on the shapes, size, and characteristics of the patient. And therefore, numerical methods are the elective way to test hundreds and hundreds of possible combinations, looking for the worst case condition. Here is represented this schematic procedure that we apply, starting from virtual surgery applied on digital models of real patients created by MRI with all the tissue represented. On these digital models, we can have simulation to evaluate the temperature elevation on the prosthetic device during the MRI scan. Well, on these last days, we just got the good news of the approval for the force loss proposal financed by the Italian Health Ministry. In this case, the idea is to generate subject-specific 3D biomechanical models of the lower limbs by use of a 3 Tesla MRI system that we have available at the Electoral Institute, segmenting MRI imaging to obtain bone and muscles and generating 3D patient-specific models. And after that, we have to combine and validate that models with dynamometry and electromyography measure that we made on patients. The clinical application in this case is the differential diagnosis of force loss in fragile elders with sarcopenia or dynapenia conditions. The project will last 3 years, starting in the next few months. Okay, that's all for the current project. A very final consideration to close my presentation is about how much I have to thank all my collaborators who made this possible. But I have also to thank the 4 directors, Armando Giunti, Aldo Toni, Susanna Stea, and Marco, of course, who guarantee support and autonomy in my research activities. Thank you again, and thank to the audience for the attention. Okay, that's all.
Okay, thank you, Fabio. Thank you very much. We can move to the next talk, entitled full field methods to investigate bone mechanics. And the speaker is Gianluca Totti. I supervised Gianluca when he was a student at the university here in Bologna, in Italy. In Italy we will say quando l'allievo supera il maestro. I think that in English it will sound like the student has become the master. Okay. Gianluca, the floor is yours.
Thanks a lot, and I'm trying to share my desktop.
Okay, we can see it.
Perfect. So, Balu or Max or Massimiliano, so thanks a lot, and yeah, I'm really flattered to be able to give this presentation and to be able to contribute to this large history. And I'm asked to talk about full field methods to investigate bone mechanics. So we did a number of other things, but I will try to keep the focus on bone for the time being. So, as Balu said, I started there. So everything started there. My journey started at the University of Bologna, and I was lucky enough to basically be part of Laboratorio di Tecnologia Medica at Rizzoli Institute as a part of my final year project. And that's me in one of my favorite activities. So as most of you can remember, and still is from time to time, less. But I had the possibility to meet a lot of colleagues, current colleagues and friends, and make friendships. And really, it was one of those moments of eureka moments that all of us are looking for, because the project, final year project, is still, sort of a moment in life where you are not quite sure what you want to do. And being part of that lab, for me, meant the eureka. So I knew what I wanted to do, and I knew what I wanted somehow try to become. And but I had to move, as many of us, to a foreign country. So basically I moved to Portsmouth, and there was an opportunity to do a PhD here at the university in orthopedic biomechanics. So the main aim was actually to work on a hip simulator that we used to have, but this hip simulator didn't behave very well. So in that time, they purchased a micro-CT, industrial micro-CT system, a Nikon, for different applications actually. And they told me, yeah, well, what you can do? And I said, well, I never used some of this before, so I'm a mechanical engineer, I know nothing about imaging. So there we are, starting in 2009 with a brand new system, knowing nothing about it. And that's why also my experience there became very fruitful, because I knew what Fabio was just explaining now, what fabulous work they've been doing. And I started to read Egon's papers and Simone's papers, and trying to get my head around to something that was completely new to me. And so, starting from there, I completed my PhD, and I did a number of other things. And afterwards, so I organized conferences, I organized symposium here with Enrico, and we did another one as well recently in a very bad place in Hawaii. So I suggest none of you can go there, because it's a very bad place. We got both injured there. And a number of other things. And I specialized in working with combination of micro-CT or tomography and in situ mechanics to try to get some more information about tissues and biomaterials using digital volume correlation, essentially. So in the meantime, I'm directing this center. We established this center in collaboration with Carl Zeiss, and so the center is equipped with latest technologies of X-ray microscope, which are lab-type synchrotron, small synchrotron, if you like. And so there's a website and Twitter, of course, and we just put there also a request for scanning requests. So in case you are interested, and we already have a lot of collaboration with most of you that I will just explain in a bit. But if you are interested, just click on that and or contact me, and there we go. But so these microscopes, actually what they can do, so they were too good not to publish something that we published in 2019, and this is an example of what this microscope can do. So basically you have this, as Cecilia was explaining, regenerated bone in vivo, so due to basically the presence of different biomaterials. And zooming in, you can really have the flavor of different levels of detail of what this new bone looks like when it is basically formed by the dissolution, if you like, or the degradation of this biomaterial that is favoring bone regeneration. Now, coming to the topic of today, so Luca explained already very, very well what this DIC is. So basically, when using optical imaging, you can get basically you need a speckle pattern, and you can get your displacement and deformation or strain field using digital image correlation, but is, as Luca explained, mainly limited to 2D if you use one camera, or if you use a set of cameras, you can get a 3D but on the surface of your sample, essentially. So what we can do instead is basically to use digital volume correlation, which is based on tomography, most of, on a 3D image. So it's either X-ray computed tomography or others, mainly X-ray computed tomography. So here it started back in the days with Bay, and then it progressed with different type of applications on starting with trabecular bone actually, and then vertebra, and then biomaterials in this case for osteochondral repair, and bone cement interface. So the application was quite new, and it was basically used with some notion of what the application could do. So how it works, very briefly, you have your imaging, you have your mechanics. I'm just saying for those of you who are not very familiar, you can do a mechanical test basically in situ, inside the micro-CT chamber in this case. And at each compression level, stepwise, you are basically acquiring a full tomogram. And then you can appreciate what is happening on your structure visually, but you can correlate all those information, and you can get your displacement field, volumetric displacement field, and your strain field. So there are two main families of DVC. I'm sure Enrico will explain more what global DVC is doing, but I'm mainly focusing on the local family of DVC softwares and algorithms, which are basically correlating independently the different subvolumes that you are using to sample your original volume. And this is how it works in terms of, it's based on a zero-mean normalized cross-correlation, and also on the assumption of small strains, of course. The small subvolumes, they have to be correlated independently, as just said, and for each one of those correlations of the subvolumes you are using to sample your original volume, you get a displacement vector, and then you can get, basically this is your resolution of the measurement, if you like, yeah, based on how big are those subvolumes you use to basically sample your original volume. The important thing is that all those subvolumes that you use, they contain enough of these balls, and these balls are the grayscale pattern that you are using to enable and to have the quality of your correlation. So that's why you cannot reduce that one too much. Otherwise, you will see only noise. And this is very important, and this is something that it is driving, or it was driving, a lot of the research that we've been doing. Because, you know, as a famous sentence of Bertolt Brecht, we are just trying, and we will have to try, to limit the error and to try to understand what this technology actually is doing and try to use it in a reliable way. So we did a lot of work in collaboration with Luca and Enrico during the years, and so basically we tried to establish some guidelines, more or less in different types of tissues and biomaterials on how to use DVC, also using different settings in terms of micro CT or synchrotron micro CT. I will give you some applications later on. The basic trend is always the same, and this is something that we always advise for the new users and for all the students that they are basically approaching this discipline to check before you are basically doing something or using this technique. So you need to find out the right trade-off or compromise between your subvolume size and the error which is relevant to your material. Because I just want to repeat, and this is a common mistake, so DVC doesn't know anything about your material. It doesn't know the material properties. It only relies on a grayscale. So you need to know what your material does and what are the constraints in terms of the yielding or the failure of your material. Now, I would like to start to show you some applications, starting from the use of DVC in clinical CT settings. So this is one study that we recently published, where we are looking at the subtalar joint. In the first instance, we are looking at the subtalar joint and trying to use DVC basically to derive or to the relative motion of talus and calcaneus, and to aid the determination of the center of rotation of this joint. Following that one, we are trying now currently to basically see what are the strains in the talus and the calcaneus. This is basically a study done with this PET-cut CT. So essentially you have a patient standing and then doing three movements, one in neutral, one in eversion, and one in inversion, and 3 consecutive scans, but it's very, very low dose, so there was no harm for the patients. In strain, I just put high and low. I don't put the numbers here because the strain error here is still under consideration with another work that we are doing in collaboration with Luca and Marco. And so basically, we are just trying to give you an idea here of the entity of how the strain is distributed rather than the actual number. It is still ongoing. Now, if you move down to some of the organs, so we did this work with Luca and Marco Palanca and Caterina and Valentina back in the days, and we looked at vertebral bodies. And we compressed them in situ, of course, and we evaluated the strain distribution with DVC. And what is always interesting is the fact that you can start to pick up basically strain and damage that then will occur essentially in the region where it started to strain. So at apparent level, or if you're looking only at the images, you won't see much. But then the fracture started to occur, actually, where the strain was appearing in the first instance. So this is just to show a little bit of the power of this DVC and to see things inside. Because also if you look at the outside here, you can see a lot of low strain. And therefore, DIC would pick something, but is not able to pick the extent of what is happening in this particular case. Going down to the tissue, so we are doing a couple of studies here, recent studies, where we are looking on your left-hand side, essentially on, basically this is bone regeneration, so it's a rack osteotomy, and then basically this femur was fixed with basically external fixators, as you can see the pinhole tract basically. And so waited for time to regenerate and forming the callus, and then doing essentially DVC on that, subjected to compression, stepwise compression. And then we can see basically that most of the strain, again, what we can learn is most of the strain is really concentrated in the regenerated bone in the callus, mainly. So there are different type of unions, of course, and we cannot generalize, but this is something that we learned from here. Also, in terms of bone biomaterial, we had another study where we had regenerated tissues, basically aided by different biomaterials. And again, you can see here how the strain is distributed in a small video during the compression, and depending also of the microstructure that these two types of biomaterials they are inducing in the regeneration process. So this is very interesting also to observe in terms of the mineral density, how obviously strain is going to basically areas of low mineral content, whereby they are favoring this or they're promoting this mechanical stimuli, talking about physiological, that then is favoring the regeneration. So other things that I'd like to share with you is essentially on some work that we've been doing again very recently, and looking at the bone or looking at the hard tissue or something that is more absorbing in X-ray is well, it's not easy, but it's easier. So looking at soft tissues is much harder. And in this particular case, what we were using phase contrast in this VESA systems that we had in order to essentially highlight some of the chondrocyte lacunae with the hope that we could use those as markers for DVC. So in this particular case, this is not an in situ test. So the samples were basically imaged and then mechanically loaded ex situ and then reimaged again. So what you see here is the residual strain really accumulated in the structure. But we could pick some of these, and also the error analysis was done. Is in the paper, and it was showing that basically these are real or something that can be considered a strain, the residual strain from the mechanical test rather than simply an error based on the error analysis that we did beforehand. And this is interesting because we are working and we will work more on this. It is very interesting because in osteochondral defects and in osteoarthritis, the role of articular cartilage and the role of calcified cartilage is still unknown, and this is one of the main topics that we are looking at actually at the moment. So these were all images and applications that we did, first on the clinical CT and then on lab systems. And now I'm showing you something that is still of very much interest, what we did on synchrotron. And these are two studies that hopefully they will showcase once more the importance of when you're taking your samples to synchrotron, you will have to check what the radiation is doing to your samples, because the radiation can be very bad and basically can alter all your mechanical evaluation if you are meant to be doing an in situ mechanical test. And this is the proof of basically having high doses or low doses that they are still inducing some strains due to the radiation, but is very much optimized in terms of what you want to see mechanically. So this type of work is really necessary, and also in the right-hand side, so a much higher resolution with in the trabecular tissue. Again, you can see cracks developing and strain field changing in the crack developing due to the radiation. So the right-hand side is basically a sample that has only been irradiated, not mechanically loaded, and this is the strain that you can see accumulating in that particular tissue and the cracks developing in there. So it is very, very important. There is work that we are doing now on trying to address this and trying to give the community some more information on how to approach this type of experiment. Another important thing that we just did recently is something that it was an idea for quite some time, and we managed to do it in the synchrotron, and some more work is on the way. So basically, continuous or real-time in situ mechanics. So this is a little bit going with a DVC and using the principles of DIC, because we imaged and we compressed mechanically, and then we image on the fly, and merging a number of tomograms, in this case up to 18. And basically then we performed DVC. Now this case, it is the 5 cycles, 30 cycles, and 100 cycles, because the cortical bone was subjected to some cycles before the continuous loading up to failure. And as you can see here from the small video that is running, when the one that has more pre-cycles, let's say, is developing something that may be multiple micro and even nano cracks, and therefore basically starting to yield before the others, and basically is not developing this main crack throughout the sample as in the other 2 cases. And this is very interesting, and this can be representing some of the future of this type of technique, trying to having the strain reading or the volumetric strain in real time rather than stepwise, as we did so far. So I don't know how I am with time, but I'm just going to basically conclude. I just wanted to show you a few things on what has been done. We did a lot more work also, on biomaterials and on different types of applications as well, and currently in soft tissues. I just mainly focus and wanted to give you an overview of what we've been doing on bone very recently. So in terms of VC, it is powerful, but like if you buy a Ferrari, you need to be able to learn how to drive it, and you need to be able to learn how to control it, and you need to be able to use it in an appropriate way. And it does a great job in giving you a better understanding of bone and biomaterials at different scales and different mechanical loading and conditions, trying to facilitate that gap in the structure function of this type of tissues. And has a huge potential to be used with different types of conditions and imaging modalities and multimodal imaging, and also in combination, as I'm sure Rico will explain later as well, with FE modeling. And but just to remind that it is a technique, so it is not the main purpose of everything. It's just something that we use, and we try to develop as much as possible to understand what we really want to understand. So this has to be, we always have to bear this in mind when we are using this. It's not the purpose of using DVC. I see a lot of papers also that I'm reviewing that where the main aim is, I've used DVC. This is not the purpose. The purpose is to use DVC to understand something else. Now, just a couple of things that you may be interested. I'm editing this special issue for materials. We published 12 papers so far, so very good. And I've anyway extended the submission to the end of this year. So if you're interested to submit your contribution, just get in touch, or just let me know. Very happy. And then so I've been invited by Marcus to give this JMBBM Frontiers webinar on the 10th. So if you would like to attend or just share to anyone that you think may be interested, so please do so. Yeah. Finally, I just wanted to say that it is not only about science. It is not only about research. It is about a lot of human relationship and friendships and collaborations, and it gave me really a lot my experience and made me meet people that I'm still in contact with, and they became very good friends, other than very fruitful collaborators, and more to come, and in the following years. And with this, really, I would like to thank again all of you for starting my journey, and yeah, happy to answer all your questions whenever you want to ask them.
During the break. Thank you, Gianluca.
Okay.
I would like to remind the chairman that they have to be chairmen. We are going over time horribly, so please do your job.
Okay. Okay.
Sure.
Okay. Thank you, Gianluca, for your interesting presentation. Okay. Last but not least, Andrea Mandrino is currently carrying out his research activities in Barcelona at the University de Catalunya. The title of his presentation is Extracellular Matrix Dynamics Due to Active Cell Forces. Andrea, are you there?
Yes, can you hear me?
Yeah, and you can see your desktop? Or...
Yeah, can you see my presentation?
Yeah.
Okay, so yes, thank you for the kind introduction. It's a pleasure to be invited here. Just a couple of slides about a little bit of my weird scientific trajectory. I was born in Sicily and I studied in Bologna, and that's the reason why I'm here. I worked in Rizzoli, and it was a fantastic period. And these are some pictures of the 15 years LTM celebration. Now we are 30, right? So what I just wanted to say, it's not very different what many have said. This was a really amazing laboratory, an amazing time for me. And in my case, it also developed a kind of a passion for biology, combination of engineering, simulation, and kind of an obsession of trying to understand properties of living materials. Then after I moved from Rizzoli, I went to Barcelona, where I did my PhD on spine biomechanics with Damien Lacroix. That was also a very nice time. We basically developed tools for patient-specific simulation of spine in the context of a nice European project called My Spine. My contribution here was to actually develop this part that you're seeing now in the movie, this mechanotransport to basically predict metabolites and their dependence to mechanical loading. After that, my life brought me to MIT in Boston, where I basically work on experimental microfluidics and microvasculature, maybe spending some word on that. And one moment. And after that, I was back to Barcelona, and where I am now. Since September, I work in UPC as a lecturer. And just wanted to tell you about this experience at MIT, because it's going to be relevant for the presentation. What we did is here to basically look at this nice model, which is vasculogenesis on a chip, where you can basically build microvascular network which become perfusable, so you can use them for making some, in my case, my project was about multicellular mechanics during this organogenesis process, but you can also use it at the single cell level to study properties of the ECM, which will be the focus actually of my presentation. What I'm doing currently, it's I moved on the basic developmental biology, try to understand how bone and cartilage are formed in the first place, and ECM remodeling. So I'm actually working on surrogate model of mesenchymal condensation, so chondrogenesis and then formation of bone in the embryo using limb developmental models in the laboratory of James Sharp. That experience is still ongoing, but now from September I'm working at UPC, so this is a collaborative thing I'm doing right now. And we're also using studying the microvasculature in the limb and doing some fluid mechanics work on the microvasculature. But today I'm going to talk about the ECM remodeling and the single cell scale. This is one example of where this remodeling is going to be important. For example, in the microvascular formation, you can see here a surrogate of the ECM, which is a fibrin gel, which gets hugely remodeled and densified around the cells during this organogenesis process. But also, if you look at disease model, like, for example, single cell cancer cell migration in stroma, where you here see basically a cancer cell in a collagen gel, you can also see how relevant is this process and the ECM, how it gets remodeled, and this process is very dynamic. So I'll repropose this video all and over, but I want to introduce some notion about it to follow me better in this presentation. First of all, you have to notice that during this remodeling of this fibrous hydrogel, there are some spikes here and there around the cells, which you can maybe see, which are called filopodia. These are probably some force acting on the ECM. We didn't know that before. We discovered that. But they're going to be important in the rest of the presentation because they are the elements that move the fibers close to the cell. Also, you can, in this movie, you can also see deformation of the fibrous hydrogel. And also another property is the stiffening. So this fiber gets packed, and you can see how the signal increase close to the cell. This is also going to be important. Okay, so what we will learn from this, hopefully from this short presentation, which experiment we can use to test this living material at the cell level, which material apply, and if we can merge it with computational model to, refine our understanding. Also, I would like to give you some flavor of the living material property that we studied, and maybe one fundamental mechanism used by the cell to remodel the ECM. So first of all, let's focus on this property, which is stiffening. As I said, these cells are kind of generating an armor around them of this ECM surrogate. So what we did, I collaborated in this very nice study where we basically use optical tweezer to probe the material stiffness at the cell level. You basically, embed some beads randomly, and then you move them with a known force with optical tweezer, and then you can basically know the distance of the beads from the cell and how is the stiffness. You know the force, you know the displacement, so you can measure stiffness. What we understood is that material is stiffer close to the cell, which will be this yellow line, and then it's less stiff far away from the cell. So the stiffness is an increase of, let's say, Young modulus as you get close to the cell. But it's not only that, because then we tested this behavior. This was nonlinear. So there is a mechanical response. You have less stiffness when the force is low, but you have more stiffness when the force is high. And this is due to the entropic elasticity and bending and buckling of this fiber in the hydrogel. So this was coupled to a computational model, which I didn't develop. That was a collaboration. And this model basically could infer stress from the actual nonlinearity of this curve. And the nice thing we discover is that the stress decays not with the cube of the distance as it would do in a linear isotropic material, but it actually decays with the square of the distance from the cell, which means implies a long-range stress propagation, meaning that the cell far away are able to sense the stress better because it propagates farther away from the cell. And that was a nice property we discovered. So how do we test this material? Well, we use a classic cell hydrogel model. We can use optical tweezer. We can couple with computational model, in this case, discrete fiber models. And the properties we are seeing, these emerging properties, are stiffening and long-range mechanical communication. But we still don't know about what's the fundamental mechanism that the cell use to remodel this ECM. So what we did here is to, let's say, invent another test for this living material. We use cytoskeletal drugs, in this case cytochalasin, which is an inhibitor of contractility, to have a no-force configuration. Then we basically, with microfluidic, we wash away this cytochalasin, so this treatment is reversible, and the cells will basically be alive again, let's say, will not block, and we'll start to load the ECM, so we will have a loaded configuration, and then we can do what Gianluca has been summarized very nicely before. We can do digital volume correlation to basically measure the displacement all around the cell. And then we can finally unload again by using, again, the same cocktail of drugs. So why are we doing this protocol? Because in the first no-force loading, we are going to look at an elastic material process, but also something else, which we would like to know. And then in the last one, from loading to unloading, it's just very short, and we just remove the force, so it's going to be pure elastic. And then by difference, we can understand what is in this question mark, right? So the first thing we understood is that as you may have already guessed, remodeling is not fully elastic. There is permanent deformation occurring after we basically unload. This in mechanics, you probably all know, it's called, it reminds of plasticity. So we were like kind of seduced by the idea that there was plasticity going on here. So with the measurement of the 3D displacement with the digital volume correlation, what we could understand is the profile of how this displacement evolved from no force to loading, and then how it gets, released elastically in the unloading phase. So that would be the elastic portion, and the total one that has been going on for all the process is going to be elastic plus some plastic component. So how do cells plasticize the surrounding ECM? Well, we understood that they need philopodia to do that. Why? How we understood that? Because we basically used cocktail of drugs that didn't prevent philopodia to happen and drugs that did prevent philopodia. And as you can see, when we have philopodia acting, we can always see this armor around the cell, so stiffening and plasticity going on. But when we don't have philopodia, we don't see it. So philopodia has to be responsible for that. So the picture is what is shown here on the bottom. We have a cell which, have this philopodia going on, which basically pull on fiber. But how this plasticity arrives? Well, a fiber model that we developed in collaboration with Michael Mark in Yale University was explained us how this could possibly happen. And the picture is the following. Basically, philopodia will grab on the fibers. They will pull with the force. When the force is too high, the fiber will disconnect from the remaining network, because the crosslink has an unbinding rate, and this fiber is dragged close to the cell. And then the cells with another philopodia will grab another fiber, and so on and so forth until these cells are packed. And this is what, in our mind, generates this stiffening and plastic remodeling around the cell. Of course, I was a big fan of finite elements, and then I say we maybe could model that in a continuum way. So basically, we use a standard elastoplastic Norton Van 't Hoff model, where you have elastic, viscose, and plastic component, and we actually introduced another feature, which was damage. So the degradation of the Young modulus, because as you saw in the previous slide, we are dealing with a material where we are basically disconnecting fiber from the network. So this material degrades. The Young modulus goes down with strain. So we plug this into this model, so we have fully elastoplastic plus damage. And then basically we introduce this in a simple axisymmetric simulation of a centripetally contractile cell and trying to reproduce the experimental condition, no force, loading, unloading, and then we could kind of recapitulate the experimental range when we actually consider that damage is also happening other than, in addition to viscoplasticity, okay? So what we have learned, well, the fundamental mechanism that we have learned is that these filopodia are rapid. This process, I didn't mention, but this movie you have seen of this process, they are like occurring in minutes, like half an hour, and the cell is already remodeling everything around. So this is a fast process where the filopodia pull and disconnect filaments from the network. So why is this important? Well, plasticity, of course, is going to be related to how the cells are shaping this living tissue, right? So this is a nice study from the University of San Francisco where they actually precisely put cells in a slab of collagen gel, and they actually could predict and reproduce experimentally the shape of this cell, of the hydrogel, due to the active cell forces, which I was talking about. These are some of my data where I also looked at the ECM around microvascular networks, so around endothelial cells, and you can see how this fibrin gel gets hugely remodeled, packed, and it also helps shaping this organogenesis surrogate model. Thank you very much for listening to me. I hope everything went smoothly, and that's it.
Oh, okay, thank you very much, Andrea.